welcome to the second video of my thesis defense talk. So last time I defined sort of the main objects and goals of my thesis. And in this video, I'm going to go into more details about what I actually did. Well, I did leave you on this slide last time of the main results that I had managed to prove. Of course, this may be a little incomprehensible for two reasons. One, the form, this nu sub r in this specific degree. So this is, some sort of a differential form. So it has some specific degree. I haven't told you what this is exactly, how to construct it, and I won't in today's video. That's going to be for the next video where I talk about the geometric side of things. In this video, I'm just going to tell you about some of the representation theory that goes into it. Namely, I'm going to tell you about the other thing I didn't define, and that is the notion of a highest weight vector. So I just want to remind you quickly is that we're working on this vector space V with a Hermitian inner product of type PQ. So that means that we can find a basis of P vectors of positive inner product, Q of them have negative. And this, we have this D of V as some manifold of negative definite subspaces on it. And I think that's all I'll mention for now. Okay, so I'm assuming you know a couple things about Lie groups and Lie algebras. If you just remember the definition of a Lie algebra or look it up, great. By the way, if anyone wants me to go into any more detail about any of these topics, just let me know. Let me know in the comments if you want a more in-depth explanation about anything. So say we've got a Lie algebra and it's semi-simple. Forget what that means. It just means it's nice. And one of the nice things about semi-simple Lie algebras is that they have a distinguished subalgebras called a Cartan subalgebra, which has several nice properties that we can infer the structure from. And inside the Cartan subalgebra, or rather in the dual, so the dual is just the collection of linear functions that eat vectors of H and spit out complex numbers. There exists this set delta, and that set delta actually splits into a disjoint negative delta and positive delta, and we call these the roots. So this is the negative roots and the positive roots of this set of special functionals. And we'll see why they're special in a moment. Well, one thing that we get out of this is, now I won't define these subspaces, these G sub alpha in this talk, but there do exist this sort of nice decomposition, which is indexed by these so-called roots. So we have these root spaces on one hand, and then if we sum those up and sum it with our Cartan subalgebra, it gives us this specific decomposition of our Lie algebra into these spaces. But this all seems very weird and abstract. Why would anyone care? Well, this is where the highest weight theory comes in. So first, we better define weight if we want to talk about highest weight. So say we've got some representation of Lie algebras, our vector space, it's acting on some vector space W, and we have some vector in that vector space W. Then we say it has weight lambda, where lambda is a functional, if the action of any H sitting in the Cartan subalgebra acting on this vector V simply has the effect of multiplying it by the number that you get when you feed H into lambda. So essentially a weight is just like a generalized eigenvalue, basically. And we're saying that, if a vector has a weight, it's in some sense a sort of generalized eigenvector. We then say it's of highest weight if, so we have this decomposition into the spaces, and these spaces that are indexed by the positive roots have this special property that if you have a vector that's a weight, well, we then say it's a highest weight if it's killed by all the action of all the vectors in these G sub alpha spaces. Well, why? But I mean, what does that even mean? Here's the theorem that explains why we care. So if you have a semi-simple complex Lie algebra G, and you have a vector V, which is of highest weight, then it turns out that if you simply take that one vector and act on it by everything in your Lie algebra, this generates a subspace of W, possibly the entire space. This is an irreducible subrepresentation. So this is good, right? Because in representation theory, we want to understand the irreducible subrepresentations. These are the atomic elements of the theory. And here's a good way to construct irreducible representations or test if your representation is irreducible. And we can get our hands on it, right? If you found this vector in your space that satisfies these certain things, this is a pretty concrete realization of a irreducible representation. Now, if you'll recall from the last time, I talked about this group URR, and so its corresponding Lie algebra is the math frac URR. And we want to do representation theory here. So we'd like to be able to apply this theorem to URR. Well, the problem is, so if you look in the theorem statement, we need a semi-simple and complex Lie algebra. It turns out this Lie algebra is not complex, but we can take a Lie algebra that's not complex and simply complexify it, by which I mean we just take a tensor product with the complex numbers, and now we have a Lie algebra that has complex scalars. And in fact, this gives us a very well-known Lie algebra. This is GL2RC. Okay, this is probably one of the most well-understood Lie algebras. But here's a problem. This is not semi-simple. Well, it turns out, okay, so no big deal. We modified our Lie algebra once already. Let's modify it again. It turns out there's a special quotient you can take of your Lie algebra to get a semi-simple Lie algebra. And well, okay, so big whoop, there's a lot of quotients you can take. What makes this special, right? Well, it turns out that if you want to understand the irreducible representations of your original Lie algebra G, there's a nice theorem. I'm not going to go into the details here, but it basically says you can mostly understand the irreducible representations if you figure out what the irreducible representations are of the semi-simple quotient. So it's this quotient by this very special thing called the radical, right? There could be many quotients that make it semi-simple, but that's what makes this in particular one the one we call the semi-simplification, because it allows us to lift these things. So in this case, the semi-simplification of GL2RC is SL2RC. And so by the same token, so you might have been worried that, oh, I'm switching Lie algebras. Well, I explained why passing to the semi-simple quotient isn't a big loss. But now there's complexification, because it turns out there's a one-to-one correspondence between the irreducible representations of a real Lie algebra and the irreducible representations of its complexification. So it looks like we're changing things unnecessarily, but we're not actually losing all that much. However, I did tell you that what we really care about is the maximal compact subgroup. So actually, I'm going to take K naught to be the maximal compact, the Lie algebra of the maximal compact subgroup. And I'm going to do the same thing. I'm going to complexify it. And I'm going to take the semi-simple part of it. So that's what I'm going to define to be this math frac sub R is this semi-simplification of the complexification of this Lie algebra of the maximal compact of the Lie group URR. A lot. And then finally, so we want to apply this whole highest weight vector thing, but now we're just caring about this Lie algebra corresponding to maximal compact. So I'm going to let delta sub C plus, this is just going to be those positive roots that belong to the cartan of this compact Lie subalgebra, so I call them the compact roots and denote it with a C. Okay, so here's a more refined version. So I told you at the end of last time what it is I proved. So this is going to be the end of this time, and I'm going to tell you the general outline of how I proved it. And next time we'll talk about the geometry and what nu actually is. Okay, so in the r equals 1 case, we have this form nu sub 1. And we're looking at it just in this specific degree 2 times q minus 1. And we're evaluating it at this certain point in the manifold. I explained this briefly last time. The idea is we can do induction. So remember, we got this P and Q that's going into the whole theory here. And I'm saying if I fix Q, I can perform induction on P so that if I have P and Q, I know that this nu sub 1 has the expected weight in terms of being a highest weight vector. In this PQ case, then I can do induction to know that it has the proper weight for all higher values of P if I'm working with that same Q. But the base case requires that P is at least 2Q minus 1. Why is this a problem? Well, if you remember last time, I told you that the very simplest case to try out by hand is the case when P is equal to 1 and Q is equal to 2, and that this is intractable by hand already. So that's like a bit of an issue. Of course, I did say I wrote some code to do this for me, but even the code slows down exponentially as Q grows. We get matrices, for example. There's some matrices that get involved in this computation that have rank 2 to the Q. So as Q grows, that becomes quite computationally expensive. Okay, the good news is, so we need to show this thing for these forms nu sub r. The good news is if you've shown it for nu sub 1, then no induction needed. We'll see in the next video, there's a very nice splitting of this form nu sub r in terms of the forms nu sub 1, and we can just lift these results directly. Okay, so we're showing that nu sub r is a highest weight vector. I've just told you my induction strategy for showing when this is for showing the weight of this vector. But the highest weight part of it, right? I know, so I've got to show that this is killed by the action of these certain special vectors. And again, we can use induction here. So if I got to fix P and I've got some, or I've got to fix Q, I've got some P, and I know that this vector is killed by the positive root vectors, then for all P prime greater than or equal to P, I can prove this is the case as well. But now our bound is even worse in this very computationally expensive thing that we're doing. Turns out the base case requires that P is at least 4Q minus 2. So that's not great, but that's why the computations became absolutely essential in this picture. And then again, in this case, it doesn't matter. Once we've shown this for r equals 2, then we can lift this to all higher values of r for a reason that will be explained in the next video. Now, you might be thinking though, well, why am I starting r equals 2 for the root thing? Why not r equals 1? It turns out in the r equals 1 case, there are none of these compact positive root vectors. So there's nothing to show. All we need to show is the vector has the right weight in that case. So I think that's going to do it for today's video. I'm just going to talk about the representation theory. Next time, we're going to return to talking about the manifold I mentioned in the first video. We're going to talk about vector bundles and Quillen's theory of superconnections. And hopefully, if the video doesn't go on too long, I'll fill in some of the last details about what these forms are and what this proof looks like. So thanks. Stay tuned. Oh, I should mention, any questions at all, just leave them in the comments, and possibly I'll make a video, going into like what are Lie algebras or something. Okay.